Now, in mechanical design, uncertainties abound. When we think about the materials that we use in a design, depending on which factory we've bought it from or which source around the world that we use, the properties of those materials can vary. Depending on the environment where we install our design, temperature can be different, corrosion and humidity conditions can change, and our parts can age over time, depending on how long they've been deployed. Our structures can also have different types of connections, whether it's welded joints or shrink fits or bolted connections, and so forth. And most importantly, the operating conditions in the real world have a variation in both intensity and distribution that is not easy for us to incorporate when we're just trying to do the design process. A classic example would just simply be temperature. You think about when you go outside today, right? Go outside today and stay outside for 24 hours. Does the temperature remain the same for the whole day? The reality is that it doesn't. That temperature varies over the course of days, over the course of hours, and even minutes. And that is something that varies stochastically. There's a lot of variation in it. And it's not something that we can just incorporate very easily into a design. So rather than doing so, we make assumptions about what we think are the critical values or the worst case scenarios, and we try to incorporate those into our design. Because there are so many sources of uncertainty, what we have to do as engineers, including the sources of uncertainty, are the simplifications that we make in our design, our equations and assumptions. We have to introduce what are called design safety factors. These are factors that we apply to our design to ensure that we don't have failure. Now, the equation is pretty simple. There are many of these factors we can use for different problems, but the basis of it is that N, our design safety factor, is equal to a material property in the numerator divided by a design calculation, something that we've calculated from our geometry and the loads that we've applied to our structure. And our goal is for that N value to be greater than 1. We want our design to be safe, the N value to be greater than 1. What that means if N is greater than 1 means that the material property in the numerator is larger than the design calculation, than the calculated values coming from our design, meaning our property, our material can sustain the loads or the temperatures that our design calls for. Now, if N is less than or equal to 1, that means our designed calculation is equal to the material property or less than it, and that means our design will fail, that our design will not survive or meet our selected requirement for safety. Now, an easy example would be just, hey, let's define the equation of safety against yielding. Well, the safety factor against yielding is the material property of the yield strength in the numerator divided by the calculated stress, the stress that is in our design. And if that stress is less than the yield strength, then our N is greater than 1, and we have a safe design against yielding. Another example. Let's look at the example for a safety against failure of our design. In this case, we want safety against failure, which is the ultimate tensile strength of our material. Our numerator is the UTS, the ultimate tensile strength, and our denominator is the calculated stress from our geometry. If that stress is greater than the UTS, then ND is less than 1 and our design fails. Now, this same framework, material property in the numerator, calculation in the denominator, is how we are able to apply safety factors to many different things, whether it's yielding or failure or fatigue cycles to failure, or even things like critical crack length, a crack growing in our structure. If it gets to a certain size, our part will fail. Well, we can define a factor of safety for that. Now, beyond just calculating if our design is safe and finding from our calculations what that N value is, we also can use the safety factor as an enforcement mechanism. For example, the FAA, the Federal Aviation Administration, the SAE, Society of Automotive Engineers, various organizations define safety factor requirements that a design must be safe greater than 1 to a specific value. For example, the FAR, Federal Aviation Regulations, requires that the ultimate safety factor is 1.5 for an aircraft, while 1.4 is used in various spacecraft. Now, the ultimate safety factor includes all forms of safety, from whether it's crack growth or temperature. Every form of safety that is possible in an entire mechanical system must meet 1.5. It's actually a very high barrier, right? And what that means is the material property needs to be 150% higher than the calculation in order for your design to be viable, for you to actually fly, for you to actually go to space. And in the case of an ultimate safety factor, that means every component in your system needs to have that 150% margin, right? Now, if we are given a safety factor, then we kind of have a restriction on what our design can sustain. So we can take that safety factor equation if we're given ND and we know our material that we're going to design with, we can then calculate what is the maximum allowable design stress or temperature or crack length that our design can have. And we can use this to then make decisions about how to modify our designs, right? So in this case, if our design calculation is less than our given material property and required safety factor, then our design is safe. And if our design calculation is greater than our given material property and safety factor, then our design is unsafe, right? Now, an important thing in design is that there can be many criterion that we are evaluated against. Not just, oh, will it yield or will it fail? But we can have many different criterion that we're concerned with. For example, temperature. The temperature cannot exceed a certain value. Or fatigue cycles. How many load cycles? How many times can we fly this aircraft before it's no longer a viable design? Or crack length. Many structures, like bridges, have cracks all over their structures. How long can those cracks be before we say, hey, this design isn't viable anymore? We need to stop. We need to shut the bridge down. It's not safe, right? So there are many different criterions we have to consider. And when we think about the ultimate safety factor, that's where we're applying safety to every possible criterion in a design, right? So now let's do one little example here. Let's say that we're working with NASA and we've 3D printed a rocket engine that we are going to test at NASA Marshall. And we want to apply a safety factor of 1.4 against the melting temperature of the alloy that's used in the nozzle, this alloy GRX810, which is the nozzle alloy in this design. Now, the nozzle's melting temperature is 1350 degrees Celsius, so 1350 degrees Celsius. What is the maximum allowable temperature? So let's set this up. Let's set up how we're going to solve this problem. First, let's identify our knowns. We are given our safety factor, which is 1.4. So we need to be safe by 140% of the material property. We're also given the material property, the melting temperature, which is 1350 degrees C. So we collect those together, and those are the things that we know. Now, our unknown is the thing that we need to find. In the case of this problem, there's only one thing we need to find. We're asked to find the maximum allowable temperature. Let's call that T max is equal to question mark, right? And then in order to solve this problem, we need to create an equation, the design allowable equation for temperature. Well, let's say the allowable max temperature, T max, is equal to the material property of melting temperature divided by the safety factor for temperature. We go ahead and put our numbers in, 1350 divided by 1.4. And now we found that the max temperature that we can allow in this design to meet our safety factor is 964.3 degrees Celsius. So if we were designing this rocket engine and we want to make sure that it is safe, the maximum temperature in this design, at least in the GRX nozzle, and maybe as well as in the ejector, that temperature must be less than 964.3 degrees Celsius.